Okay, well, thanks very much, everybody. I think we probably ought to get started. We've got a really busy afternoon, and there's about 4 other things on this afternoon which are of interest to people who are also interested in imaging, so there'll be a lot of coming and going, but hopefully there'll be plenty of interesting stuff. We've got a really excellent program this afternoon. So this is the first annual meeting of the Centre for In Vivo Imaging Sciences, which is here to help everybody who's interested in imaging get their research done. So the afternoon is structured so that the first session is about what is becoming very interesting, sort of 3D printing and the capabilities that opens up for printing tissue structures. And we've got 2 excellent speakers who are going to explain about that. In the first coffee break, there's an opportunity to see some demonstrations related to this and also to do some networking, but particularly some of the materials that are being generated for replacing bits of bone, etc. We then have a session on proffered papers, hearing about what's going on around Edinburgh as a whole, and by that I mean both University of Edinburgh and Heriot-Watt University. The third session is particularly to update you on what's happening. Make sure you know where to find the information that you need, how to get your studies started, where you can find additional educational material about learning about different imaging techniques, etc. There will be some prizes awarded. We have an excellent judging panel, and thank you very much for giving up your time this afternoon to come and do the judging. And then there's more refreshments afterwards, which is, I realise what you've all actually come for, but I'm sorry, you're going to have to do some work first. And do go and look at the posters, because that's also where you can find out about what sort of things are happening that might be of use to yourselves. I just wanted to highlight a few things that have happened in the last year. It's been quite a big year for imaging activities in Edinburgh. There's a lot of new grants that are of considerable relevance to imaging, even if some of them are not directly about just imaging. One of those, which many of you will be aware of, is the award of the Farr Institute, which is to do with health informatics. And one of the outputs of that is going to be to take the entire collection of images which have been obtained on patients in the Scottish National Health Service and download them so that they can be accessible for research purposes. Massive job, but really huge opportunity. Several very large grants from the EPSRC have been awarded for various interdisciplinary research centre activities, super resolution imaging. Some of these are led more by Heriot-Watt than by the University of Edinburgh, and vice versa. Some are specifically in Edinburgh University. Some are about oncology, different topics, really wide-ranging and fantastic achievements, and also some really important MRC awards. I'm very pleased to say that our 2 Imaging Prize studentships have now started, and hopefully they will be helping on microphone duties. Xenios and Daryl are here. Thank you. Thank you. Wave. Say hello to everybody. The Imaging MSc has now launched alongside the Neuroimaging for Research MSc, and currently there are 70 students across both programs, and those are being extremely well received from the feedback so far. We've made considerable efforts to try and join up the administrative processes between the 2 human imaging facilities. Duncan Martin is now responsible for administrative activities at both sites, and hopefully that's helping to streamline processes and facilitate other more efficient working and opportunities. And there's some important publications that have come out across a number of fronts. I just highlight a couple of them. One was to do with setting up a world standard for imaging some aspects of really important brain disease, and the other one, which of course you'll all be aware about from just in the last week, the new method of imaging vulnerable and ruptured atheromatous plaque in the coronary arteries, which is far more specific than other methods that have been used so far. So really big, important outputs. These are just a couple. There could have been all sorts of other ones that I'd highlighted, but there we are. This is a little map of Edinburgh, and I just drew it very quickly, but it gives some indication of just how joined up the different imaging sites are. This, of course, is not just human imaging. It's pre-clinical imaging. It centres in psychology and the art school in the central area. It includes Heriot-Watt and the Roslin campus, areas to do with informatics, the Royal Edinburgh Hospital and King's Buildings, and it makes quite a pleasing and rather symmetrical little diagram which shows the increasing collaborative activity that's going on, highly multidisciplinary and very positive. So without more ado, I would like to hand over to Professor Charles French-Constant, who's going to chair the first session, which is about implications of imprinting for imaging.
Okay, well, thank you very much. My name's Charles French-Constant. I'm Director of the Centre for Regenerative Medicine on the other side of the hospital. And as a regenerative biologist, one of the things that's very clear is that whilst we're extremely good at thinking about ways of making different cell types from the stem cells we work with, we've made really rather little progress thus far in the critical issue of making a tissue, which of course ultimately is what we would like to do. And one of the problems is that we're stuck in what I call the two-dimensional phase of science, in that we tend to work in dishes. And it's very, very important going forward that we start to think and work much better with three-dimensional structures, both to look at the effects of three dimensions on cell behavior, and of course taking to the next level to actually use that technology to create the shape that's required for tissues. So we're going to hear now a couple of talks that are really taking this on, taking advantage of some of the opportunities offered by three-dimensional printing.
Thank you very much for the introduction. I have a little bit of a cough, but my talk is a really short one, I will try not to cough into the microphone. So, the College of Art and the Veterinary School got together on a project about using 3D printing for veterinary students, and also using it with the art students. And the background of this project is that in the veterinary world, we use live animals extensively for teaching, to bring our veterinary students up to speed in their clinical skills. And some of that is totally fine, but there are always issues in undergraduate teaching from ethical issues. So you don't want to overuse animals when you don't have to teach them all sorts of practical, surgical, and other skills. And even if you do, if you have a cohort of 150 students, even if it's just something like palpation or things like that, it's not really fair on 2 or 3 dogs or 2 or 3 horses. So you have to limit your resources. You have limited resources to do these things. And for some of those things, 3D printing might be a really good alternative. Another aspect is health and safety. As you could imagine, our patients, they kick and they bark and bite and everything. And so if you have a big cohort of students, you're responsible for them. So if they are for very specific tasks, areas where you wouldn't need live animals, that would be an advantage. And also time efficiency. If you think about, like, if you use, for instance, cadaver parts, you have to get them out of the fridge, put them all over, everybody has to be gowned up and everything. So there are also the other aspects that make the live animal or animal parts not so practical. And it's also very expensive to provide for 150 students or so, each of them dead animal or dead animal parts, for instance, or living animals to work with. It's just not very easy. And this is in particular an issue in the preclinical years. You know, we don't really have any intentions of removing our live patients from teaching. But what we would like to do is we would like to teach our students in the earlier part of the curriculum on models that are not live animals or not post-mortem specimen, so that they can learn the skills already, so that we can then, when they're in their final year and have to deal with live animals, can do this with less effort. So this is the background of this project. And to achieve those goals, we have a clinical skills committee where we're trying to develop these kind of prop-up models where students can learn certain skills. Catriona Bell is the head of this model, of this committee. And we look into all sorts of options of replacing live animals and post-mortem specimen with alternative materials. And some of these things are purchasable. We just purchased a big horse where you can do rectalization and everything. Some of these things are very expensive. And there's not such a big market as I would imagine there is in human medicine, where you just have one species, many more students. It's way easier for you to do this. One way of getting around this is we could just, print out some body parts and then use them for printing, for teaching. And that would be a really good addition to our clinical skills lab that we already have. And in this, one of the things is that is spatial understanding for the veterinary student. It's very important because that links the theory and the praxis for them. It's all well and good to flick through a book and look about a kidney on a picture, whereas if you really have to sometimes understand the three-dimensionality. For a lot of things, particularly for surgical skills, that's very important. And then one additional thing is, I get occasionally giggles or strange looks on it, but this is not something we made up, is basically that studies have shown that women have a harder time in 3D comprehension than men. It's like in 3D gaming and things like that. But our students, we have about 90% of our students are female. So we have another reason why we want to make the whole 3D comprehension better to help our students. So we would like to have 3D models for anatomic specimens to make that better. And what we do is we have a CT scanner on site, which CT, as you all know, is pretty much good for almost every body part. It's my favorite imaging modality. And we can make digital models, 3D models from that, different technologies, surface rendering, volume rendering, of everything. So we can make something for the students to look at 3D structures. But that's not the same as doing something with them, having your hands on it, drilling holes in it, or whatever you want to do. And of particular interest is the surface rendering software, because that can be used to make 3D printing. So this is an example of a canine head that we made a surface rendering module of the whole head here. And here is just the skull. It's very easy to make this with the software that we have. And you can choose what you want, soft tissues, bone, or you can have a combination of both. So this is a 5-minute job to make this. And then we use Osirix, at least on some of our workstations, and we can there easily export a surface rendering module in different object files. And some of them are useful for 3D printing. So that's why we came to the College of Art, and we started a collaborative project with them, who has an experienced print master, Richard Collins, which will do the second part of this talk. And we found that we have a crossover interest. For the veterinary students, we want this to improve their clinical skills. And for the art students, strange animal body parts give them a source of inspiration. And so we applied for a grant for the University of Edinburgh Principals Award, a teaching award for use of 3D printing to help both of these groups. And we were lucky enough that we got this grant. And that's what we're doing now. We're doing the 3D printing, working with art students and with veterinary students. So we use mainly CT data, but we also wanted to compare this to photographic techniques, where we print out different body parts. So far we have done vertebrae, skull, lung bone, teeth, kidneys, both normal and abnormal ones. And we've involved veterinary and art students in making and working with these printed objects. Jason Ferber-Grant is one of the students who's doing a project on it. He's here today. He did the main work on this. And then basically was our first one. This was a mouse gag for a cattle. And this is canine skull with just some scaffolding material in it in different sizes printed out. And here's an equine tooth. And just going to show you the tooth. So this is a magnified equine tooth. What's that, 122? It's a 122 module. And it has a tooth root infection, so you can kind of see the lack of the root there. And that's what we're working on, and we will later on assess that for students teaching, how good they are. But we have some of those modules here, so in the break, please come down and have a look and touch them. And I will hand over to my colleague, Richard Collins. I'd just like to thank all my collaborators on this project who did far more than I do on it, which is mainly Jason, but also our teaching Dean Susan Rind, who helped a lot with this, getting this project done, and all my colleagues from the art school as well. So I will hand over now.
Thank you very much, Tobias. Thank you, Professor Charles. My background isn't in biology, but before talking about the collaboration with the veterinary school and the considerations that developed, I think it might be worth giving a little bit of context to how we use 3D printing at the art school. So last year, there was a new development where we opened a digital prototyping CAD/CAM suite within the art college. It has laser cutters, CNC routing, surface scanning, and it also had a 3D printer included. Now, we use that in collaboration with more traditional forms of making. And 3D printing, it offers great opportunities for our students to abstract, to represent, to form prototypes, and to really understand an object. Often, when you're thinking of an image, you can draw it as many times as you like, but until you make it, until you think around the corner, you haven't really understood how it would come together. So just a little overview of our kind of 3D printing or additive manufacturing, starting with a three-dimensional design or object, creating a digital model from that. And that digital model is made up of very simple geometric surfaces. At that stage, we could calculate a support, and that support is made up layer by layer of toolpaths. That can then be printed or made in layer by layer technology. So here we have a 21st century representation of a 20th century bust. Our printer, it's very similar to the most common available types of 3D printing, extrusion. As Dr. Xu mentioned, it's very similar to squeezing toothpaste out of a tube, or if you've ever used a hot glue gun. And you can, in this case, use ABS, which is a thermoplastic really common in car bumpers, Lego bricks. And what's key about it, you heat it up to a point about 100 degrees, and it starts to flow. And when it flows, it can be extruded with pretty good accuracy. Fusion deposition modeling is by far the most common form of 3D printing. If you hear there's a £1,000 3D printer that you can buy, it's probably this form. It's relatively simple technology where you're heating up a material, most commonly ABS or PLA plastic, and extruding forms layer by layer. So as it's a simple technology, generally you're looking at quite simple forms, especially with the very basic machines. There are other types, many other types of 3D printing, which were touched on already. There's digital wax printing, there's selective laser sintering, And these use different forms of technology to construct a model one layer at a time using different materials. But what I'll be talking about today is just using the one material, the ABS, and the support material that goes with it. So here's a snapshot of our machine. And the top part gives you the X and Y dimensions. So it will draw or print out one layer of the model. Then once it's finished that layer, the bed will lower down by 1/6 of a millimeter in our case and allow you to print the next model. So you can see here, speed it up, but that's it, just building up a model one layer at a time. The tray at the bottom's removed, and that should give you a rough idea of the overall size that we can get up to with our machine. Whenever we're building, the scaffolding that we're using, it's very similar to ABS. It flows at the same temperature and it's laid down in the same thicknesses, but what makes it, well, useful for this application is it can be dissolved in a caustic solution. So we put an object with support into that wash tank. The solution's heated up to about 70 degrees. It's bubbled around, and all of that support structure can be removed away. Now at the ECA, we have various different schools that are using the 3D printer. Architecture and landscape architecture using it for formal investigations. In the School of Art, we've got painting, sculpture, and intermedia that are exploring possibilities of its use. Within design, we've got product design, is quite a big user, but also jewelry, glass, and also fashion and textiles. Our approach to 3D printing, or some of the more common approaches, is looking at the technology as a way to understand form, surface, and scale. You can get, in terms of design, pretty good accuracy and precision. You can also get very complex and delicate forms and interlinked objects. So both of these parts, the chainmail, if you like, was printed out as a solid piece. The support was dissolved, and those links are already interwoven. Also, the hinge printed as a complete part. Now, this is a very common example, but if you notice, it's a little executive toy, if you like, but whenever it was printed, it came out looking a little bit like that, where you had support in between all of the moving parts. So it offers great opportunities for designing and design freedom. You can also use it to develop quite simple forms. These are little push connectors, which could be used to clip together two separate parts. And if you find the one on the right is a little bit too loose, then you can thicken that up. And I guess what I enjoy about the 3D printer, it brings the designer and the maker, the manufacturer, much closer together. So you can look at a problem or design, print it, see if it works, and then revise from that. For example, we had a part of our CNC writing machine wasn't really fit for purpose. So I was able to measure it, design the part needed, and print out a better piece. So then the opportunity came for the collaboration with the vet school, and I found it very exciting. With the CT scans that we were receiving, there was a lot of highly detailed information, which if I was to try and model that from scratch, would be there for weeks. The forms in itself, here we have a dog's vertebrae. I find them quite compelling and quite interesting, and also structurally would be quite significant. So if we're looking at a digital model, I think this is where I would start highlighting some considerations that biologists or medical or veterinary practitioners should think about when they're looking at using three-dimensional printing. I guess a lot of times if you're getting something 3D printed, it's going to be sent via or through someone like me who's a designer. And there's some considerations that I think you should bear in mind so that, well, you have greater control over the end output. For example, this digital model is an STL file, which stands for Standard Tessellated Language. Basically, no matter how complex the form is, it can be broken down into triangles. So whether you're making something from sheet metal or something from 3D printing, a triangle's always the safest, most reliable form for understanding the geometry. Whenever we started looking at the CT information, preparing for 3D printing, we started to find we needed to prioritize the information that we had. It wasn't as simple as putting it through a program and saying, okay, I want this to be printable. We needed to start to make some critical decisions over what to really investigate. In order to make something printable, it's got to be a watertight mesh. What you see at the minute here, I've colored the back face orange. So we've got a surface with no thickness. So there's no volume here. It would be impossible to print that. When you put that into a 3D printing program, it wouldn't know what was the inside and what was the outside. So you would have to do some form of repair or patching, closing up holes, getting rid of any naked edges. And with this case, it's quite straightforward what I needed to close up. But a lot of the times with the other examples, we needed to decide what is information that we're keeping, what should be printed and what should be ignored, what is abnormal growth, which does need to be shown, and what is just an extra bit of digital noise. Whenever you're looking at a digital model, there isn't a right and wrong answer over what level of detail or what's a good file and what's a bad file. In this snapshot, the original model has close to 900,000 individual faces, which would make it very difficult to process and to print. Already, I've reduced it to 25%, and it still has a lot of the characteristics as before. I could reduce it again, and each time I'm reducing it, I'm making it easier for me to print, but it'll get to a stage where it's losing its form for what the input, or the person inputting rather, requires. So with an example like this, although this is one of our earlier figurative scans, it would be a good point to discuss where we would take the original information and represent it or represent it in the digital form. Whenever we're printing, and hopefully if you want to see any of the models, you'll see some of the examples, there's an outside skin that's formed, and inside that you can fill it in with a solid structure, but that would take a long time, especially at the volume that we're using, and also use a lot of material. So it's possible to fill in the interior of a model with a low density. Now, depending on what you're wanting to use the model for, if it's for an educational tool and it needs to be strong, then you need to think where there's flex and where there's strength. Going back to the original CT information, there's an example here of equine tooth, I believe, and as well as having the outer surface forming a mesh, it's got an inner surface also forming a solid within that solid. Now you could ask that to print, and it would print exactly what it sees there. So it's got an area inside which it sees as a gap, a cavity, which it would fill up with that brown support material, and then it would enclose all of that support material with modeling material. You take that out, and there's no way to get to that interior. There's no way to remove the support. So although that's quite a simple example of two forms, you can imagine if you're wanting to create a surface, there's a certain amount of abstraction that you'll need to do to that model. And if it's left to just be processed by someone else, again, you're losing control over what is kept and what is important. Whenever you're printing, especially at the scale that we're printing, orientation becomes really significant. This model was printed, that was the bottom, and then it was built up in layers like that. This model was printed with this base. Now, this type of structure, because we've got material running right the way along its length, is much stronger than this one. Also, visually, it's much more attractive. Now, you always will get the chance for print failure. So what's happened with these models, whenever it's been building up these columns, there just hasn't been enough of a connection between quite delicate parts. And where the machine has tried to put down some material, there's nothing there to put down on, or it's hit a little bit of debris which got clogged up. So then the next bit goes down in a wider spool. You end up with something very like a bowl of spaghetti. So moving forward, I think this collaboration will be very useful in looking at digital models and how to really look at the digital information and enlarge and focus on what's the important points. We've done quite a few samples so far, and I can see, well, hope to see it being productive in forming a kit of parts for students, understanding form and scale. We're only printing in a representative material. We're not printing like for like different materials, but even so, we are printing models which can be useful for a variety of applications, and hopefully education is one of the main ones. So one of the latest examples, we were looking at the ear canal of a dog. And when I took the model that you've seen earlier, I had to work out how to split that and how to print it. So did I print it just in a very kind of, crude way where I've taken a slice, cut out that section that I need, and closed it up? Or have I given that structure a thickness? And again, that's an area where you'll need to discuss and investigate what is the best option for 3D printing, because 3D printing is like another form of manufacturing. It's taking an idea and making it. But there's a lot of considerations for how you make it, how the prototypes will develop. And as I said, please feel free during the break to have a look at some of our samples. Thank you.
Fascinating. Any questions, anyone?
Thank you very much. That was really, really impressive. I wish I was still a student and had access to all these models. Obviously, the advantages and the applications for teaching are vast, and that's fantastic. Obviously, in the regenerative medicine field, the holy grail is to be able to build patient-specific organs, replace lost material in a bespoke way. But before we get there, there's an intermediary where I can see already you could start using this for planning complex elective surgeries, particularly for neuroorthopedics. Perhaps, taking a CT scan of a patient that you're perhaps planning an orthopedic procedure for, building, printing a model of their joint or bone, and then planning that surgery before going in, and ensuring that you get a better outcome, or even using the material to test force and stress and things before that. So are you thinking about that sort of application? Are there ways of maybe just starting with bone material, producing something that approximates the properties of bone, so that you can model that before doing a surgery?
Yes, well, one of the more recent discussions with Tobias was if there was an opportunity where you needed to, let's say, put a plate into a skull, and you just get, obviously the one opportunity to do that for real, but if we could print out a one-for-one representation of the form, put the plate in place, see if it will work, even aid the procedure of how you would fix that for more complex joints, then I think I could see that happening tomorrow. So it's very exciting from my point of view.
So Lego bricks are all of one consistency, but obviously tissues and organs are lots of different consistencies. So to what extent can you print a structure where you not only have a three-dimensional complexity, but you also have areas of different consistency, different stiffness?
Well, I guess it comes back to what Dr. Chu was saying about the different printer heads and forms of extruding or hardening materials. The example that we're using, you're just using the one material, same density, and you're having to be clever to make something flexible or hard by how that works at a structural level. But there's nothing to say that you couldn't be using multiple nozzles. So rather than just extruding in a model material and a support material, you're using several different nozzles. And rather than using the quite crude pushing out glue approach, you've got other forms of hardening that type of material. So you could, for example, there's a form of digital wax printing where you've got a vat of resin and lights used to harden it layer by layer. So you can get really, well, in my experience, really great resolution, not in terms of cells, but I could see that being developed further.
But can you see a day where you could actually sort of make a hand that a surgeon could practice on, where the consistency was really quite similar to the natural consistency?
I think if you were able to break it into a kit of parts, one option is to print or try to print the hand as one complete part, but maybe that's not the most kind of intelligent way to pursue it. It might be better to print the bones as one print and then form a method, and it could be just going back to traditional forms of casting where you have a poured silicate that goes into that, so that you have the hard 3D print inside with silicon around it. Obviously that's a very kind of basic example. Well, it depends what's more difficult for you to do. Like, it would be very easy for me to say to a student, okay, we could 3D print that, or you could make a hole in that material using clay and pour in a silicon. And I know that's a very kind of hands-on approach, but the same, I guess, thinking from multiple directions at how you make it could be applied.
Just building on your question there, Charles.
Hang on, just if you don't mind.
Sorry, just building on Charles's question there. I guess there's a whole complete new science here around material science, and are there groups of sort of polymer chemists who are working on, because in theory you should be able to construct the hand that you've just envisaged, but it needs a whole new set of, well, I don't know if it's a new set of polymers and those polymers already exist, but it must be possible. And my question is, do you know, are there groups out there that are doing this type of work?
Well, there are groups working on this, and I think the most famous thing you probably heard about is that people 3D printed a gun. And as Homeland Security in the US went on to and shut it down, the website now. And so there's a lot of interest in a lot of different areas to work on it. And I just recently read in The Economist, actually, that in the University of Glasgow, they created a 3D printer for drugs, which also wasn't received all positively. And that was very recently. So, but there's a researcher there, maybe one of you knows more about it, but they basically, you can print certain drugs as a cocktail, and that obviously could be legal or illegal drugs. So there's a huge amount of research just spinning off. And in terms of use for medical practical use, like you suggested, these companies starting to exist already now. So there's, it's called the 3D printing show. It was in London. I didn't have the opportunity to go, but they come back. I think that's really a good thing to go.
Yeah, just take the microphone.
A few of us did attend that 3D printing show in London, actually. I guess in response to a couple of the comments that have been made, there are some medical applications that are currently ongoing. A lot of max fax, facial reconstructive surgery, for example, custom dental implants, which are already currently being manufactured by one or two of these companies. And we certainly looked at 3D print manufacturing where you can have a range of materials with one or two different color types, for example, so you can print out models that have different structures you can see, but also different levels of plasticity as well, going from a solid structure to something which is quite pliable, with two print materials where you mix them together to get a mix of translucency and opacity and also plasticity. So, and certainly there are a couple of companies, Scots's for example, who are printing out with a resolution that's better than what we're currently generating with CT anyway. But it does seem to be a very evolving technology, so I'm sure that within a year's time we're probably looking at multiple materials, multiple levels of plasticity and solid structure. But certainly there are people using it for medical applications currently. Mostly it seems the dentists have really kind of picked up on this because they're doing a lot of CT scanning and they're looking to build solid structures for implants. And there's been a little bit of work on that. And it was a very good print show.